In this video, we're going to write some more similarity proofs, specifically those that are focusing around the side angle side and the side similarity methods. If you haven't watched the videos on side angle side similarity and side similarity, you're going to want to do that before watching the video on the proofs. Let's go ahead and get started. In number 1, we're told that segment ZP is perpendicular to segment XY. So I'm going to go ahead and mark some right angles in my picture. And we're also given some side lengths, which have already been marked for us in the diagram. And we're being asked to prove that two triangles are similar to one another. I find it really helpful to, anytime I'm trying to prove triangles similar or congruent, take a highlighter and highlight the triangles that we're dealing with. So there's the first triangle, XPZ. The second triangle is this guy on the right, ZPY. Those are the two triangles we're trying to prove similar. I want to take a look at the similarity statement for a moment and just notice that X in the first triangle matches up with Z in the second triangle. So those two angles are going to be congruent to each other. And at this point, I'm noticing that the orientation isn't the same on both triangles. So what I'm going to do is redraw these so that their corresponding parts will match up a little bit more easily or a little bit more clearly. So I'm going to start with the green triangle, and I'm going to draw the green triangle exactly as it appears in the picture. This is Z, P, X. And then I'm going to go ahead and I'm going to rotate and flip over the purple triangle so that its orientation is exactly the same as the original triangle. So I want the right angle down here in the bottom right-hand corner. And we said angle X corresponds and matches up with angle Z, so I'm going to put angle Z in the bottom left, which means that angle Z in the green triangle is going to match up with and correspond to angle Y in the second triangle. So this is my Y up here. And then I'm going to take the side lengths that were given to me in the original triangle, and I'm going to draw them below. We said this was P, the right angle. Z to Y, I need to go back and change. Z to Y is actually 9.6. So now I've matched up the corresponding parts, and I can get a little bit more clear picture of exactly what I'm working with now. Now that I've separated and resketched these triangles, I can see pretty easily that the side angle side approach is going to be the one that I'm going to want to use for this particular problem. So I'm going to do a little outline down here. And in my outline, I'm going to talk about the pieces or the parts that I want to use in my proof. I'm going to use those right angles as my pair of congruent angles. And remember that we're not proving triangles congruent now, but rather similar. So rather than having sides that are congruent to each other, we're going to have sides that are in proportion. So what I want to do is take and compare side XP in the first triangle with its corresponding side ZP in the second triangle. And I want to take and compare side ZP in the green triangle with its corresponding side YP in the purple triangle. So this is my outline. These are the pieces that I want to talk about here in my proof. So I'm going to go ahead and probably get those angles out of the way. That's the piece that I'm most familiar with and most used to. I'm going to go ahead and start by proving those angles are congruent to one another. And in order to do that, I'm going to use the perpendicular lines. So I know these lines are perpendicular due to the fact that it's given to me that these lines are perpendicular. If those lines are perpendicular, I know that angles 1 and 2 are right angles. And now that I've established the fact that those two angles are right angles, I'm all set to go ahead and conclude that they're congruent to each other. So my pair of angles on my little checklist is done. Now I need to go deal with the ratios of the sides. And even though this seems a little scary or intimidating, it really isn't so hard. I'm going to begin by talking about the side lengths that were given to me in the original information. So XP is 15, PY is 9.6, and ZP is 12. And I know those are true statements because they were given to me to be true statements. And now all I'm going to do is I'm going to take my side lengths and I'm going to substitute those into the ratio. So if I compare side XP to side ZP, and I substitute in their corresponding side lengths, 15 to 12, as a fraction in simplest form, this ends up being 5 to 4. And likewise, I can do the same thing for the other pair of sides that I want to use. If I compare the length of side ZP to the length of side YP, well, that's 12 to 9.6. You might say, well, how do I simplify that, Mrs. McCann, so I can write it as a ratio in simplest form? My advice to you would be just go plug this into your calculator, substitute it into your calculator, and hit enter. Your calculator will tell you 1 1/4. So as far as a reason here, I can think of a couple different ones we could use. I've seen some teachers who say ratio of the corresponding sides. Since all we're doing is substituting in numbers for side lengths, I'm going to use the reason substitution. But if you wanted to say I'm comparing the ratios of the corresponding sides, that would be okay as well. And now, since each of these ratios is equal to 5/4, I can go ahead and set the ratios equal to each other. So I know if I compare XP with its corresponding side length ZP, that's the same as the comparison between ZP and its corresponding side length YP. And this too is a simple matter of substituting equals for equals. So my reason down here would be substitution. So at this point now, I've established the fact that these two ratios are equal to one another. I've got congruent, or the angle between those pairs of sides, congruent. Now I'm all set up to use my side angle side similarity method of similarity to prove these two similar to each other. So my two triangles are similar, and the reason for that, side angle side similarity. So there's the first example. At this point, if you have questions or I said something that didn't make any sense, my advice would be to write it down in the margin or jot yourself a quick note to ask me the next time that you come back to class. In the meantime, I'm going to move on to the next example. This one is a little bit more straightforward in that both triangles that they're asking us to prove similar already have the same orientation, so we don't have to mess around with doing any of the rotation or flipping the triangles over. We're trying to prove triangle ABC similar to triangle CDE. And again, the corresponding parts have already been matched up quite nicely for us here. So I'm just going to go ahead and in the picture, I'm going to label the side lengths. And the fact that we're dealing with 3 pairs of side lengths is a big indicator to us here. And that in this case, we're probably going to use the side-side-side similarity. So if I'm going to use side-side-side similarity, there's 3 ratios that I need to establish. I need to compare AB to its corresponding side. I need to compare AC to its corresponding side. And lastly, I need to compare BC to its corresponding side. So those are the 3 ratios that I'm going to write. But just like I did in the first example, I'm going to begin by starting with those side lengths that were given to me. And those I know because they were given. So if I compare AB to CD, That's 12 to 9. Or as a fraction in simplest form, 4 to 3. Comparing AC with CE, 8 to 6. Again, as a fraction in simplest form is 4 to 3. And then the last pair of sides I want to compare BC and DE. And again, for a reason here, I can use ratio of the corresponding sides, or I'm simply going to say I'm substituting in, substitution. And now, because all three of these ratios are equal to 4/3, I know that when I compare AB with CD, I get the same thing as when I compare AC with CE, which is the same thing as when I compare BC with DE. And this I can say all ratios have the same value. In particular, all three of them are equal to 4/3. Because all ratios are exactly the same, now I can go ahead and say that the two triangles are similar to one another. And as for my reason, that would be my side-side-side similarity. So as always, my thanks to you in taking the time to watch the video. I do want you to take a few minutes to summarize the key ideas and the important takeaways just so that you have the important understandings from this video, and then see if you can solve the problems on the next page.